Okay guys, I just wanted to run through a couple of examples of one-dimensional motion with you, just so we can start to get the hang of how we're using these kinematic formulas. So remember, in the last video, we discussed these kinematic formulas and how they each have 4 parts. So in order to use one, we need 3 pieces of information plus one thing that we're looking for. And the list of those things should match up with one of these 4 formulas. So let's kind of see how this works in action. So here I have an example of horizontal motion, and this is also going to help us to establish how exactly we solve any type of problem in physics, right? This is the breakdown of how it works, no matter what type of problem it is. First, the first thing I do anytime I have a question is I'll read through it and I will draw a picture, okay? So I have a car starts accelerating from rest at 12 meters per second squared, okay? How far will it travel after 4 seconds? So here, the situation that we're working with is we have a car. There's my car. And it starts from rest. Okay, so this is an important keyword that we're going to be using a lot throughout the course. From rest means it starts. Okay, so this means that my initial speed, my initial velocity is going to be equal to 0 meters per second. Okay, it starts from rest. It starts from a stopped position. Okay, so we have a car, starts from rest, and then it starts to accelerate. Okay, so I can write again here, just, oh sorry, I wrote in my acceleration there. So I have 0 meters per second, and I have an acceleration of 12 meters per second squared. I don't know anything about the velocity in the meantime, but I know my initial velocity, my acceleration, and I know one other thing here is that 4 seconds later, okay, so 4 seconds later, some time is going to pass, and my car is going to be, this is kind of a little ghost car, it's going to be somewhere farther forward, right? But I want to know exactly how far this car is going to be 4 seconds later. So the way I do this is I will set up a little list of my 5 variables here. Okay, these are the only variables that we know right now, the only variables that we have in any formulas. So I'm just going to go ahead and write them all down right here. Okay, now remember, there has to be one thing that I'm looking for and 3 things that I know. If I fulfill that condition, I can pick one of our formulas. So let's start filling in what we know in these variables on the left-hand side. I know my initial velocity, okay, this first variable right here, I know what this is. This is actually 0 meters per second. Great, okay. I don't know my final velocity. I know I'm accelerating, but I don't know what my final velocity is. Okay, so what I'm going to do is, I'm just going to put a dash here. I don't know what this is. Acceleration, I do know what this is. This is given to me in my problem. 12 meters per second squared. Now, there is something very important when we look at our problem here that is going to make things a lot easier for you guys, okay? And that is remembering your units, okay? Units are super, super important. So I can tell, if I just look at this problem, and I don't know anything about, what's going on, I can already tell by looking at 12 meters per second, this has to be some kind of acceleration without even reading that it says it's accelerating at this, right? Because sometimes the wording can get a little bit confusing. But without even reading that, I can tell that this value has to be some sort of acceleration because the units. Remember, my units for acceleration were meters per second squared. Only acceleration has those units. Velocity does not have those units. Time does not have those units. Displacement doesn't have those units. if you see a number like 6 meters per second squared, you can already write somewhere down there, I don't know what it is, I have no idea what's going on, but this number, in our case 12, is an acceleration. Okay, so this will help you out a lot, guys. So I know my acceleration, it's 12 meters per second squared, this is good. Displacement, I don't know it, but if I look at my problem here, it says how far will it travel? This right here, how far will it travel, is describing some sort of distance, some sort of length, right? This is a displacement. So for us here, I can say that I don't know what this is, but this is what I'm looking for. So this counts as one of my 4 variables because I need to have one thing that I'm looking for and 3 things that I know. Okay, and if I go through here, the last variable here, I only have 2 pieces of information so far. I don't have everything that I need yet, except I also know that 4 seconds are going to pass by. So very good. I can write this in for time. It's 4 seconds. So now that I have this, I have initial velocity, acceleration, displacement, and time. So if I look which one of my kinematic formulas has initial velocity, acceleration, displacement, and time, we can kind of look through these. If I look at number 1 here, initial velocity, good. Final velocity, this is not good. We don't have this. So we can't actually use number 1. And actually, anything that has final velocity in it, we can't use it because we don't have this information. So we can't use number 2 either, and we can't use number 4 either. But if I look here at number 3, the one that does not require us to know what my final velocity is, it has initial velocity, good, we know that. It has displacement, good, that's what we're looking for, all right, that's one of our variables. Acceleration, we know this, and time. For us, this was 4 seconds, this is good. This formula right here satisfies everything that we know and what we want to know. So what I'm going to do is I'm just going to write in my formula right here. So I have my displacement is equal to my initial velocity times time plus 1/2 acceleration times squared. Okay? And this is really good because we want to know what displacement is. So normally you might have to do some algebra. Let's say I was trying to find out what my initial velocity was. I would have to take all of these variables to the other side, right? So I would have to do this. But since we're looking for displacement, we're lucky here. We don't have to do any algebra right now. This is already by itself. It's already set up for us to solve the formula. So what we're going to do is we're just going to plug everything in. So this now is equal to my initial velocity, which was 0, times my time, which is 4 seconds, plus 1/2. My acceleration here is 12 meters per second, and my time again is 4 seconds, now squared. So 0 times 4, this whole thing is just 0. 0 times 4 is 0. This is good. This leaves me with 1/2 times 12 times 4 squared would actually give me 16. Okay, and if we plug this into our calculator here, so we can do this, and we will get, let's see. So if you're following along with me, you can also work through this. I got 96, I believe. So I'll go ahead and try that one more time just to make sure. I have 96. All right, so 96. Now, an important exercise for us to do here, now that we have this, is to check. We need to double check what's going on. What is the unit of this? This is the displacement. What is the unit? It should be like how far something is. And we've solved for displacement. This is actually 96 meters. Okay, so this is it. We've solved the problem. So the way we work this out, again, guys, just super quick breakdown of how this works is first, I draw a picture. Make sure I understand what's going on in the problem. Okay, Then I highlight all of my information, and sometimes I use it to kind of annotate the picture, but you don't need to do that. What you can do is you can take this information, everything that you can extract from the problem, and start to list out your variables on the side and fill all that in. This thing right here is super, super important for us, guys. If you can build this thing right here, you'll probably get the answer right. That's it. Okay? This is actually the hardest part here for most of our problems. Once we do this, we identify what pieces of information we have and what we're looking for, and we can use that to choose a kinematic formula. And once we have that, we can plug in our values and solve for the value we're looking for. In this case, it was displacement was 96 meters. Okay, so now that we have that, I want to go through one more problem with you guys, and that is an example of free fall, vertical one-dimensional motion, right? So we've tackled one-dimensional motion horizontally. I want to do one more example with you guys vertically. So in this example, if we read through this, I have a ball that is dropped from a certain height. This is a height of 6 meters. And I want to know how long it's going to take that ball to hit the ground. So for vertical one-dimensional motion, hopefully you guys saw this in the slides already, but if I have an object that's in the air, okay, let's go and switch back here. Say a ball, it's in the air, it's not touching the ground, okay, then there are certain things that I know about this, right? So first, I've already drawn my picture here. It's very short, easy to draw. What I'm going to do is I'm going to annotate this a little bit because I know how far this ball is from the ground, right? It's 6 meters up off the ground. And that's all. If I just take one glance at the problem, it looks like that's all I know, right? I have a height of 6 meters, okay? Height, remember, is describing some kind of length. This is a displacement. But I know that I'm looking for how long it will take for this to happen. So time is actually what I'm looking for. I have a displacement value. This is 6 meters. But these are only two things. I need to know two more things here in order to solve this problem. It looks like this problem doesn't give us much of anything to work with. Okay? But there are a few things here. Another case here where we have vocabulary kind of telling us what's going on is that this ball is dropped. Okay? The ball is dropped. It is not thrown, it's dropped. So if you let something go, right, it starts from rest. If you throw something, then when it leaves your hand, the moment you stop touching it, it's moving at some speed, right? But if you drop it, all you do is you let it go. So you let it go, it starts from rest. So if you drop it, it starts from rest. That means this, okay, let's kind of just draw a little arrow right in there. This also means that my initial velocity is 0 meters per second, okay, if it's dropped. So this is 0 meters per second. All right. And now we have two things that we know. We need one more thing. We need to know one more piece of information in order to solve this problem. We don't actually know how fast this ball will be going when it hits the ground, okay? So we don't know this. But acceleration is something that we do know. When you let go of this ball, it's under the influence of one thing and one thing only, and that's gravity. Okay, so remember, whenever something is in the air, if it's not touching anything, we're not going to be considering air friction in this class. It's just a little bit outside the scope of what we're going to be doing. So we can assume that gravity is the only thing pulling this ball down to the earth, and gravity has a certain acceleration it exerts on everything all the time. And we're going to define that here is acceleration, due to gravity. Okay, this, super important, is negative 9.8 meters per second squared. approximately negative 9.8, right? So this value here, anytime you have something in the air, it is accelerating downward. Downward is where I get this negative from. I just mean downward versus upward here. And how much is it accelerating? 9.8 meters per second squared. Okay, so this will be a good practice for us. Whenever we have something in the air, you know it's acceleration already. We're going to get into this more in 2D motion, some more practice with it. But for now, let's just use this value. So I have my acceleration is 9.8 meters per second squared, and it is downward, so I want to put negative. Technically, it doesn't matter if you put upwards or downwards, anything can be. But what you need to do now that we have motion and we're starting to look at, let's say, forward versus backward or upward versus downward, we need to make sure that all of our values have the same sign for the same direction, right? So what this means is if I say downward is negative here, I have to check all my other values and make sure that anything else that is downward is also negative in order for me to get the right answer. So if I look at this ball is actually moving downwards. So if it travels 1 meter or 2 meters, it actually does that downward. It's moving from here, it's moving downward 2 meters, 3 meters, all the way to 6 meters. So this displacement is actually going to be negative 6 meters. It's going to be in the same direction as gravity, right? So let's go ahead and update this. We'll put a little negative right here. We have negative 6 meters for our displacement. Usually, guys, if you get an answer that's like a negative inside of a square root or something like that that gives you an error, it's probably just because there is a negative missing for something moving downward, right? That's the most common case for all of my students here. Okay, so let's kind of check out what we have and what we're looking for. We have initial velocity, we have acceleration, displacement, and time. Okay, so we've got 4 values here, and I think actually these are the same 4 values that we had in number 1. We had initial velocity, acceleration, displacement, and time. Okay, that's not on purpose. It just worked out this way for us. So we know that we're going to be using the same formula. If I come up here and look at this, what I have is initial velocity, displacement, acceleration, and time. Let's go and use formula number 3. Again, the good thing here is that all of these formulas work exactly the same. So I can use equation 2 or equation 4, and it doesn't change anything about the math that I'm doing, right? Let's go ahead and paste this in here. So we have our handy equation 3 to work with. But this time we're not looking for displacement. This time we're looking for time. So make sure that once we start plugging everything in, we have to have a goal here at the end that we're going to be solving for time, not displacement. So what I'm going to do here is I'm going to plug everything in because it's going to make it a little bit easier to work with. If I tried to solve for time right now, I would need to use my quadratic formula, right? I would need to use this special form of equation 3 where time is already by itself. This is kind of long, and I'm not going to need that this time because something pretty nice is going to happen here. And this will happen a lot when we're doing our vertical motion problems. So let's go ahead and plug everything in. I have my displacement is negative 6 meters. This is equal to my initial velocity, which is 0, times my time, which I don't know what that is, plus 1/2 my acceleration, which is negative 9.8, and time squared. Okay, so looks pretty good so far. Again, because this is time and this is time squared, this could be a little bit tough to work with, but because I have 0 times time here, really nice, we get to say, or we get to cross this out. Let me cross this out one more time. Because this is equal to 0, right? 0 times anything is 0. So now, if I kind of shorten this up, I have negative 6 is equal to 1/2 times negative 9.8 times time squared. Now let's get t by itself. The way we're going to do this, let's do some algebra now, is I want to first get rid of, just a moment, first I want to get rid of this half here. I want to take it to the other side. So if I have something divided by 2, the way I'm going to get rid of this, I'll do this in another color here, is multiply both sides by 2. This half and this 2 will cancel. And I will end up with 2 times negative 6, which is negative 12, is equal to negative 9.8 t squared. Again, do this in the way that's most comfortable for you. You don't have to follow exactly the steps that I do here. Okay. Last thing here is this 9.8. I don't want this attached to my time. So what I'm going to do is, since it's 9.8 times squared, I'm going to divide both sides by negative 9.8. Perfect. This is negative 9.8 times t squared, right? So to get rid of it, I divide. So we've got this, and this will leave us with negative 12 over negative 9.8. Let me go ahead and let's calculate this right now to simplify it a little bit for us. We have 12 divided by 9.8. This should give us about 1.22. So 1.22 is equal to times squared, just in case you're following along. Hopefully you have the same answers that I do here. Remember, if you have any questions at all, please just send me an email and I can help you out anytime you're stuck. But we're not quite done yet, right? Do not write your answer as 1.22 here. Okay, you're almost there, but not quite. Yes, t is by itself, but not really, right? Because it's attached to this little square here, this exponent. We don't want this, right? So what we need to do to get rid of a square is we need the opposite of a square, which for us, I'll do this back in my other color, is a square root. So I'm going to square root both sides. This square root and this square will cancel, and what I will have here, I'm just going to flip this around, is t is equal to the square root of 1.22 seconds. Okay, and we could do this here, square root of 1.22. This will give me 1.1. So again, I usually just round to 3 significant figures. So this should give me time is approximately, I'll put these little wavies here just to note that this is approximately 1.10. So in 1.1 seconds, this ball will travel from a height of 6 meters off the ground, okay, all the way down to the ground, right? 6 meters being, about 18 feet, about 20 feet. And this is how this works, okay? So we have 2 examples now to kind of look at where we try to take some information from our problems, write down our variables, choose a formula, and solve for an answer, right? So hopefully this helped you out, guys. And we're going to be using this to do a lot more practice, especially in 2-dimensional motion. So if you have any questions at all, please just let me know.